when we set out to make this filter, we were fully aware that most students haven't seen filter theory yet. In fact, it gets taught to you kind of in the last weeks of EK 307 and also in signals and systems classes and other classes. And they're really elegant ways to solve the problem that we're trying to solve in the frequency domain. But because we don't have that knowledge yet, we can't really use it. And we don't want to impose that on you. But I could take a different approach to it. If we think of the differential equations for the RC and the RL circuit, if we think of the RL circuit, which really has an analog in the CR circuit, which is the one that we're talked about that we're going to implement in this design, or what the output voltage is equal to, is really the derivative of the difference between the input and the output voltage of the circuit, weighted by the time constant. So it's a little bit of a different way of thinking about it. But if we think about this waveform right here, this is the waveform of the breath signal. It's not DC, right? It's not a step function. It's kind of in between, right? It has a slope to it, and it almost looks like a triangle wave. And the circuit that we're building, the CR circuit, is a bit like a differentiator. It's not quite a differentiator. It's a non-ideal differentiator, but it takes an input and it gives you the differentiated output. And so here, if we have this rate of change of voltage versus time, it's going to give us some sort of derivative of that on the output. And the weight of the derivative is really part of the time constant, which in this case is the RC product. Now, if we want to choose a reasonable RC for this particular circuit without getting into too much of the math, what we can do is, we know that in an RC circuit, after one time constant, we've decayed 37% or to 37% of our initial value. And if we think about the RC time constant in terms of the periodicity of this waveform right here, we can make it kind of a loose approximation and say that if the time constant is set to the period, basically the length of time between these repeating cycles right here, we could use that as our RC time constant to design our filter. So in order to figure out what the period is, we could use the cursors. So first I'll set my X1 cursor on this waveform right here. Set my X2, my other time cursor at the peak of this waveform. If I look at the delta, it's 2.84 seconds. The frequency's 0.35 hertz. So that's saying that, say if we chose a time constant that's approximately 3 seconds, we know that over 3 seconds the waveform changes so much that it's not going to totally diminish. But at the same time, it's going to block a lot of that low frequency drift. Like if you remember from previous oscilloscope graphs, the low frequency drift would be barely moving like 1/10 of a division. It would be across this whole screen right here, which is 20 seconds. It would only be moving just a fraction. So that signal is very slow, and so the differentiator is not going to respond to that, but it will respond to this relatively faster breath rate cycle right here. So I'm just going to throw that mark down in the sand, using the kind of a lab bench approximation, and say, okay, if I make a time constant for my CR circuit of 3 seconds, we're going to probably get some decent filtering out of that. And as I said, later on, we're going to learn the formal mathematically correct way to do this, but now we're just trying to get it done.